Okay, so the course is called Production Operations and Facilities Engineering, right? If I'm not mistaken. So that's also abbreviated as POFE. Okay, and my name is actually Associate Professor Milan Stanko. Okay, and I come from a university called NTNU, which stands for is in Norwegian, so it doesn't exactly Norwegian University of Science and Technology. Okay. And the way, so I'm teaching writing on the tablet. We always, in production, we like to sketch and we like to make calculations. Okay? You can argue, in engineering, it's not very good to argue with someone just with words. Because you can really, if you're a good talker, you can argue almost anything, almost any solution, even though it's not the best. So it's better just to show with a sketch or with numbers why the option that or why the solution that you're proposing is better than the other. Okay, can you see okay the screen there? Yeah? Okay. So let's talk about production production. Okay. So hello. If you see, we have a source, right? We have a source of reservoir fluids that we call a reservoir. Okay. But it's an accumulation of oil, gas, and has water. And then I have to take all of those fluids from the reservoir all the way to a place where I end up with stabilized fluids. Okay, I get oil and I get gas. And usually that part is called a processing plant, something that has the purpose of either converting the oil to just a barrel, something that I can transport, right? And gas, something that I can put on a pipeline and send further, either to a power station, either to a cement plant, either to load these, bombonas. Yeah. Do you have bombonas also here? Do you have bombonas also here? That you store the gas and then you go and burn it, you make barbecue, you use it for cooking. How do you call them here? Yeah, how do you call these things, these containers? Much? Yeah, these bottles. Okay, I thought you called it bombonas. Okay, so we have, from that process that we have the reservoir, all the way we have something in between, which are, if we put it very schematic, we have wells that are the things that you stick into the formation, you stick in the reservoir to drain the reservoir. Okay, so you have wells, okay, and you have a bunch of equipment. Wells, I guess you took already courses in drilling. So wells is not something that is simple, something that is very complex. And then we usually have to take to this processing plant, we have somehow with different complexity a network where we commingle and take that to the processing plant. Okay, so production engineering is basically covering from the near wellbore formation. We have to know how, we are not so concerned about the long time effect, okay, what is going to happen with this reservoir when we drain after 10 years, how do we recover more oil and gas from this reservoir. We are concerned about how the well is going to produce, okay, how much rate are we going to get from the well. Okay? And then we have flow. If we can say here, summarize, we have flow in wells, flow in flow lines, flow in pipelines, and this we call the gathering system. Okay? We are gathering the production from different wells, putting it together to take it to the processing plant. And of course, production engineering takes part sometimes of the processing facilities. Okay? In general said, that's the domain of a production engineer. So this is near wellbore formation. Okay. We have the flow inside the well when the fluid is flowing upwards from the well, from the subsurface up to the wellhead. Then we have the flow in the flow lines and the flow in the pipelines, basically a pipe, a circular conduit that I use to carry that production from the field. That's what I call the field, to where I'm going to process that. Because I cannot just sell the fluids right away the way they come from the formation. I have to stabilize it. I have to be sure that I can put it in a barrel, and that barrel is not going to change with time. I put it in the tanker, I ship it, send it everywhere in the world, and I'm going to get the same oil with the same characteristics and the same gas. Okay, so there are three tasks that we told is the domain, okay, of production engineering. Okay, and I just want to call to your attention that it's very wide domain. It's a very wide domain. We have flow in equipment, we have flow in pipes, that is very important, but we have to understand the formation, what happens here when you're very close to the well. We have to understand what happens with the flow in the well. We have to understand the flow in the, and then we have to understand in the processing plant. So it's very wide, and production engineering, a production engineer has to have like the ability to look at the whole picture and see what is the most important for the case that you're dealing with. So my page is so, yep.
Website. On flow in wells.
Near wellbore, flow in flow lines. Okay, so I call this, we will see now how do we make a distinction, okay? But that's a flow line and that's a pipeline, what we have here. Okay? So the tasks of a production engineer are to understand the subsurface. Okay, we have to understand what we have down there. Not only the amounts, not only the pressure, but we have to know what are the characteristics of that formation. How much can we produce from that? How much gas and how much water we are going to produce from there. So we have to understand the reservoir, basically. Okay, and for that you have to rely on reservoir engineers. Okay, but the reservoir engineers are occupied about the whole reservoir. Production engineers, we are usually very occupied about what happens just a few meters, a few feet from the well. Okay, that's, you will see later, but that's really what determines the production of the well. So that's one thing, and it's very central and it's very important. Okay, the reservoir. So this is the production mechanism. Okay. Productivity of the wells, Okay? The second thing is to monetize the development. Okay? It's not only enough, sometimes you have very big accumulation and you have a very productive reservoir with good characteristics. But the problem is where that to connect it to a market is far away. So it will take a lot of time, a lot of effort, and a lot of money. It will be very costly to connect those big reserves that I have, that in principle they are very lucrative, to connect it to a market. Okay, so that's that's to produce reserves in a way that is economically viable. Okay? And then the last part is to optimize the development. Okay? And optimize can mean many different things, but it's basically I already have a system, I understand the subsurface, I have done a solution to monetize, to try to produce it, start to get money, and then I want to optimize the development. Okay, I want to make it to produce as much as possible, reducing the cost, with as less as possible cost. Maximize revenue, okay, reduce cost, okay. For example, reduce failures. Optimization can mean many different things. Reduce failures. Okay. But basically, I already have a system, and I want to improve it. I want to make it as economic as possible. Okay. To monetize. To monetize. Okay. Monetize to make money. To hacer dinero, ¿no? To make money. Monetize. Money maker. Okay, so before we go into to the, I just want to so that we are clear with the nomenclature, okay? Because we are going, production engineer has to know the whole system, okay, how it looks like. It has to know all the parts of the system and have to use a nomenclature which is common for all of us, okay? Such that when we say, we pinpoint to a place in the production system, all of us know what are we talking about, okay? So let's talk first about well architecture. Okay. So how do we draw a well? Okay, we have, remember for the production engineer, we are just going to look at, in the drilling process, we have that they have to drill all these casings, right? All these intermediate holes. For the production engineer, we really don't care too much about that. Okay, we just care about one casing, that's the casing that we call production casing, right? And that's the one that is in contact usually with the formation, right? And that can have different ways. You can have it cemented, you can have perforated, any way. But I have, so let's say my reservoir is someplace here. Okay, and I have my production casing. Then after that, what do I place inside the casing normally? Okay, a tubing, right? Another piece of pipe that I'm going to, here I have the surface. Let's put here a person, just, okay, to be sure that's the surface. And so that's what I call the tubing. Yeah, and that's my casing. And what size is typically the production casing? You remember? 9 and 5/8, right? Tubing, it varies very much from place to place, okay? Tubing, a bigger tubing will be, and we will see some of the logic behind how do you choose tubing size, okay? One, the first criteria, well, it should fit, right? 9 and 5/8. It cannot be bigger than 9 and 5/8, of course, okay? But we have different sizes. We have 2 and 3/8. We have 3.5, okay? We have 4, we have 5, we even have sometimes 7, okay? And that's part of this course, okay? Just to try to discuss how do we choose why tubing is so important. Okay, so how is the flow in the well, typically? Here, I made a mistake, right? What mistake did I make? Okay, I should have an annular valve. Okay, normally I make a hole here, and I took away the casing. But I have an annular valve. Okay. And the thing is that I can produce my well either from the tubing, so it will flow here and then it will go up inside the tubing, or it will flow through the annular and then will flow through here. Okay? The most typical configuration is I flow through the tubing. Okay, so how do we call this point here? Let's start to put names. The bottom of the well, right? Bottom hole. Okay. And that's very important, and that's the first point that we have to define. Okay, the bottom hole. It's just the point in this case, the point that is in front of all perforations. Okay, and you will say, well, perforations might be very long. Okay, might be a few meters, might be a few feet. So it's just we can have some freedom where to define it. But we say, well, we are going to define it in the mid of all perforations. Okay, in the center of all perforations. Assuming that you have, for example, flow coming like that, like that, like that. Okay, what is the next point on my system? Or what else should I include on my well? Okay, now comes the interface of the well with the surface. Okay, the only way I can control the well, I cannot send, I don't normally send someone here to do control here, but I use a structure that I call the Christmas tree, right? So what does the Christmas tree contain? So first I have one valve, right? How do I call it? Lower master valve? No, we have finished drilling. Okay, you have to get rid of all of your drilling information. Okay, this is production. We care about when the well is producing. Okay, so lower master valve. Then we have another valve, which we have the upper master valve. And what is the purpose of having this master valve? To close the well, right? I have a problem, I close the well completely. I stop production. And I have two: redundancy, and one of them is usually manually operated, the lower, and the upper is usually automatically operated. Okay? But these are on and off. I cannot just go leave it halfway and then go have lunch. Okay? I have to, if I'm going to move it, I have either to open or to close it. Very important. Okay? On off. That's why I mean about that. Next, what do I have? Something called the wing valve, right? I have two valves that are called wing. wing valve, and it's also an on and off valve. Okay. And to access the well, what do I have typically? If I want to access the well, I don't want, because when I take this structure, right, that's what we call the Christmas tree. Okay. I don't want to take, if I have to make a small operation, right? If I want, for example, let's say I want to go and measure the well, or I want to go and I want to see if there is any hole in there is a leakage. Okay, if there is a hole in the tubing. I don't want to have to bring a rig. Remember, to put the BOP, you have to remove the Christmas tree, put a BOP, and then go inside and access the well. If I want to make a small operation, I want to have a way to access my well. Okay, a way to send things inside the well to make small operations. Okay, small intervention. And for that, I have this valve here at the top that is called our driller friend, they should know. What do we call this valve? The swap. Okay, swap valve. And that is also on and off. Okay. One typical operation is that I open it, I lower some sort of, I don't want to spoil the drawing, but I lower a wire line with a meter, okay? For example, a pressure meter. That's what we call production logging. And then I lower it down along the well, and I go and measure pressure and temperature at different points, okay, to try to determine different things. Okay, if I have a leakage, if I have many different things. Okay, so that's what my swap valve is for. So how do they look like and these valves? How are they constructed? If we're going to make a drawing of these valves, how should we make it? Okay, these are typically gate on-off valves are gate valves. Okay, gate in the sense that you have a port. You know how a gate valve is, right? No? Okay, I have something like this. Okay, and I have something like that. Okay, here I have the main pipe. Let's see if I make it. Okay, I have my pipe. I can have here, usually it's not like that, right? But I have to have here some screws, okay, to fix it to the body of the valve. But here I have, so my valve has actually this surface. Okay, and here I have similar on the other side, okay? Okay, so what I have these areas, and then I have to gate. Okay, that's why you have the name gate valve, because you have a gate that is going to lower and is going to close. When depending on the vertical position of this gate, it's going to close or open or impede or permit the flow of. So you have something like that. When it's aligned, and here I have something like this. Okay, the space is not that much. Okay, that's a very bad drawing. make it a bit thicker. Okay, and I have here a mechanism to pull it up and down. Okay, that usually have to rotate several times. Okay, I have like a screw. So when I want the flow to, when I want to have flow, I have to align the gate with the holes that I have on my valve. Okay, when I want to stop the flow, that's something I can do. Maybe you cannot do it. Okay, let's see if I can do it. Maybe not. Okay, I have to get rid of that part here. Okay, so I just come with this structure. And pull it up. Okay, it should have come with all the rest. Okay, but you pull it up, then it's blocking. Okay, and the very important thing is that you have to, these two surfaces, they make contact. That's where you have the seal. Okay, so if you have a side where you have high pressure, the pressure tends to push all of that slab, okay, all of that gate, and tries to push and make contact between these two. Okay, so you will have the seal actually on this contact area and on that contact area. Okay, or the opposite, if you have the flow on the other side. So what is something very important about gate valve, about on and off? It should be always on, okay, or it should be closing, or it should be opening, okay? You shouldn't have midway, okay, because otherwise you are trying to create too much friction in this area where you have the seal surface, and you might destroy it, okay? That's actually where you have all the seal, what is impeding, what is protecting the rest of the system, okay? So let me just put it here. And here I can go bring it up and down. What else do I have? So what do we call this point here? Okay, the wellhead. Yes? Okay, so that's the point where we call, at least in production engineering, we call the wellhead. Okay, so you have to remember bottom hole, wellhead, I don't have anything else in between. And what comes usually after the wing valve? Okay, remember, any of these valves are made to control my well. Okay, all of these valves are either to close it or open. Okay, so why would I want to, to have, here it looks like I have too many valves, right? To close my well. I have this one, I have this one, and I have this one. And here I have the main pipe, let's say. Okay, so why to have so many valves? That it seems like they have the same purpose. Okay, and these are only on and off. This has nothing to do to control. If I want to reduce the rate or if I want to increase the rate, I cannot use any of these valves. They should be, because of the way they are constructed, they have to be either completely closed or either completely open. Okay, so one of the reasons is to measure this pressure, okay, wellhead pressure. That's something very important for production engineers and something that we can get a lot of value out of. Okay, if we manage to measure wellhead pressure, okay, that's something that has a lot of value. But to measure that, so if I close, I'm not allowed, because of integrity reasons, because of safety reasons, I'm not allowed to put just a pressure transducer here, just below the master valve. Okay, because that opens a potential leak path. If I make a hole, okay, then I might have a leakage there. So I created a leak path. So the reason why I have these two valves, this is the main barrier, protecting the well, everything that is below the surface with the rest of the system. Okay, I have two barriers for reason, redundancy, one manual, one in case automatic, one the other fails. But then if I want to measure that pressure, I need another valve to close, right? Here I can make this pressure transducer. Okay, so to measure that pressure, I can close this valve. Okay, and then I can open this one, and it will measure my pressure, the wellhead pressure. Okay, so let's put here wing is to measure shut-in wellhead pressure. Okay, and after that we have the control element of the system. Okay, how do we call that? We sometimes make it like that. I think it's not going to fit, so let me put it slightly different. How do we call the main control element of the well? The choke. Okay, is what I use. That one is to regulate. Okay, that's the choke. And it can be, we are going to talk about choke later this week. Okay, we're going to have a separate class on that. But it's a valve that I can adjust. Okay, it's something like, if we look at, so let's put here a start. Now it's getting a bit crowded. This choke looks something like that. Okay, in a very simplistic way. Okay, in a very simplistic way. So if I lower, okay, I have less space, it's creating more pressure drop, and if I take it up, then it's liberating, it's creating less pressure drop. Okay? Okay, so that's like, to be on the same page, that's where we have the wellhead. We just care about the wellhead and the bottom hole, but there are some very important reasons why to have so many valves. Okay, these two redundancy, one automatic, one manual, these two to measure wellhead pressure, that's something we want, and these to control the rate, and this one to access the well. We cannot do less, okay? We have to live with all of these valves. And if we have flow through the annulus, we have a similar collection of valves, okay? A similar arrangement of valves. Lower annulus master valve, upper annulus master valve, we have wing annulus valve, etc. Okay, so to not make it messy, I'm going to just stick to this drawing. So that's the choke. That clear? Yep. Okay, and keep this in mind, this type of valve. Actually, when we move it up or down, we should have a pressure balance. Okay, let's say if the valve is closed, okay, we should have, because it's making contact, these two areas, okay, when it's closed, it's in contact. So when you have a high pressure on one side and a low pressure on another side, you have a lot of friction. And when you try to bring it down, you can damage, okay, you can actually scratch this seal surface that you have here. So usually when we open these valves, it has to be balanced pressure in both sides. Okay, that means if I have my well is closed, I have to increase the pressure somehow with a hand pump or something such that the pressure is balanced, and then I can open the gate valve. Okay? Okay, that clear? Yep. Okay, so now let's go to another concept that is also very important in production. That is a production manifold. And the production manifold, it has many different functions, okay? But one of them is to route, okay, or to direct the production of a well okay, to certain either flow line, to certain separator, okay? Usually these big, the processing facilities are indicated here. They are not just made of usually one train. We will see at the end of the course, but it's not just one equipment. You have sometimes equipments in parallel to take the capacity of the whole field. Okay, so you cannot just rely on sending one well just to that equipment. You have to have the option to send an equipment to one separator to another separator. So that's the intention of one of the purpose of the manifold. Okay, route, direct the production of a well to a destination. Okay. The other reason why I have it, which is very important, is to perform testing. Okay, well testing. We will see now some fields you just can do testing just with a production manifold. Okay, so how does the production manifold looks like? So if we have a well, right, we can make it now much simpler. We have our collection of valves like that. Okay. So we have here a manifold. And let's say we have another manifold. Okay. And one manifold is connected to, let's say, a separator. We call this separator A. And we have another separator called separator B. Okay. What I was mentioning before. Inside this house that I call here, I have two separators. Okay, because that fluid comes a mixture. That's the first step. I want to take out the oil from the gas. I want to separate both. Okay, so this manifold is located to that separator. Okay, so what do I have to put in place between that well, okay, and this system to be able to send this well at will, okay, to separator A or separator B? What do I need? Okay, first I need two lines, right? Two flow lines. I need a line going here and a line going here. After I have the two lines, I have to have a control element, right? Something that allows me to change to select either one or the other. And that element is just simply a valve, yeah, an on-off valve. Then these two are combined, okay? And then I have another very important element that I need, that is a check valve, okay, a one-way valve. Okay, so just say we want to produce well 1 to separator A. What do I open? What do I close? Simply, right? Just open this valve, close that valve. Okay, I want to do the opposite, close that valve, open this valve. Send to separator A or B. Here. So now you have your first exercise, take paper and pen, and you have to do the same now but for two wells. How that looks like if I have two wells. I have here another well, 2. Okay, how do I connect this to that system? To either separator A or B. Okay, just on trees. Do I need another flow line like that? Imagine that this I'm, let's say, 2 kilometers. Okay, the wells are in a remote place, and I have 2 kilometers from there to the separator. To place these flow lines costs money, these pipelines. Okay, 2 kilometers of flow line, it might be 5 inch, 4 inch, it's expensive. It's not something I want to do for every well. Okay, so I should use the same. Then I have this system that I didn't put the name, but this is called a header. Okay. Header B and header A. Okay, it's just basically a piece of pipe. And this piece of pipe, you have this flow lines connected. So just try to make, let's pause now, and I just.
Sorry, Professor. The header is the same with the.
Okay, so first I say, I come here, right? Then I connect to this manifold, okay, to this header, and then now I connect to this header. Yes? And there I have the option, okay? So here I have, if this one is For that well, if this one is closed and that one is open, this one will be closed and this one will be open. Yes? You're going to get another homework, so don't worry if I spoil the fun for you.
Just
So
one question. I think that how do we call it? It's the manifold or it's a simple fold?
from here all the way to here,
Yeah.
that's what we call the production manifold.
Okay, so we have
Everything is the production manifold. The header, the combination of valves, that's what we call the isolation valves. Okay? And the manifold will be, sometimes the check valve is included in the well, sometimes not. And that will be my production manifold. Okay?
so in order to
Where?
you know what you check valve, isn't it? The one
Yeah, the other also needs, I forgot to paint it. Okay? And you need the check valve just what happens if both of them are connected to the same head? Okay, let's say here. That happened in a field I was working. Okay? Let's say both wells are connected to this header. Okay? But you have one well which is much more powerful, has much more production than the other. Okay? Let's say this well has a pressure of 300 bar and this pressure has a pressure of 100 bar. What might happen is that you might have actually that well won't be producing, but will be stealing production. You will be injecting the oil from this well back into this well. So that's why we put the check valve. Unless we can make sure that they have similar productivity, similar pressure, but if not, I always put the check valve. Okay? Just in case.
so the function of the check valve is just to give one depth.
Check valve is like come in. Yes, come in. Okay, check valve, if we look at the ball type, right, will be something like that. I can flow on this direction, I cannot flow on that direction. Okay? Just in one direction. Okay? Okay, so why do we have two separators? Sometimes we have three, four. It becomes a mess. Why do we have so many separators? The first answer is to test the well. Okay? That's the most important. Why do we want, if we commingle all the wells, let's say to the same header. Okay, you have header B. Yes, all of them are producing to this separator. I want to know how much each well is producing, right? For if here I'm getting, let's say 6,000 barrels, maybe I'm producing 5,990 from this well, and I'm producing just 10 from this well. So why to keep producing from that well? Okay. Or if I'm producing a very small amount, it might be that well has a problem. Okay. So the first reason is to test the well. Okay, I want to test how much it produces. So in those cases, this separator is not called A and B, but it's simply called test separator, okay, and production separator. Okay. All wells normally will be producing. If I want to test well 2, I close this valve, open this valve, and test it. Okay. It can be a day, it can be a few hours, maybe that's something that typically is done by some fields do it every 2 weeks, some fields do it every 6 months, depending how. And that might also depend, for if you have a well here, which the owner is Eni, and this well here, the owner is Shell, yeah, you are using the same separator. But they want to split at the end the money. Okay, they are producing 10,000 barrels. They want to know how much do you pay back to Shell and how much to Eni. Otherwise, you're going to fight.
When you say test, referring the amount or the quantity of production.
Exactly. You put here on this line, you put here a meter. Okay, I call it M. Okay, and I meter, an orifice plate, for example. Okay, or here I use a turbine meter. So I measure what is the flow rate of oil and the flow rate of gas. And I report it. I put it in a report. At this time, 29th of October, I did a test and I obtained that my well 2 is producing 3,000 barrels. And I calculate, that's something that we call allocation. Okay? Okay, production allocation. Okay? And that's basically just to determine how much, if I have this system, my allocation will be, so here I have Q total, right? Q total, some rate, let's put it just Q total. Q total is made out of the well 1 plus well 2. Okay. So I go and measure, and my allocation factor, it tells me is Q1 divided by QT for 1, and F2 is equal to Q2 divided by QT total. Okay. If I say this is 10,000 barrels, right? This is 3,000, and this is 7,000, then I get a factor 0.3 and a factor 0.7. One for Shell, one for Eni. That's how much I split the money at the end. I go, sell everything, and then from all of those dollars, 30% for Shell is 70% for Eni. Okay, very important, the money, okay? That's, you can say, to make it more efficient, all kind of things, you like to test, like to get information, but at the end, it's very important to split the cake, okay? To see who is going to eat what. Okay? It might be also sometimes that you have huge amount, right? You have a production that you cannot take just with one separator. You have to put 2 in parallel. These separators, usually you can make it bigger and bigger, but they will be very expensive. It's sometimes cheaper just to have 2 that each one has the same capacity. Okay? And then if I'm producing, let's say I don't have only 2 wells, but I have 10 or 20 wells, I produce some of them to one separator, some of them to another separator. Okay? Not to confuse you, but might be some cases that some wells that are here, that are producing to a separator, they might have a high water cut or a high GOR. They're producing too much gas. Okay? So you want to put some of those wells to that separator to balance out, such that the 2 trains, what we call the 2 separator trains, have the same, for example, gas or the same water cut. Okay. That clear? Yeah. Okay. And there is one more thing we have to say before. And that has. Oh, so let me show you. I have a figure of. Okay. Okay. Here we have. Let's say these are. Let me put it a bit bigger. Okay. These are the wells. Okay. All of these pipes, they come from the well. You have the check valve someplace far away from you. So, can you tell me what is the test manifold and the production manifold? Header? Do you see the header or not? In our drawing, how the header look like? Okay? If you see, the header was a piece of pipe that was receiving a lot of pipes, okay, from the well, right? So, where is the header here in this figure, in this picture? Okay, this one, right? One header, and here you have the other header. Just a piece of pipe with other pipes entering, okay, from the well. Where do we have the isolation valves or the routing valves? Okay, from here goes the well one, right? Here this goes to the test separator, that goes to separator A, okay, or set production separator. Here comes from well. If I want to produce to test, open this one, close this one. Okay. If I want to produce to production, open this one, close this one. Okay. So that's a production pipe. I think this is a field in Libya. Let's see now about this one. That's a field in Colombia. Okay, where is the production from the wells coming? From here, right? With black lines, 1, 2, 3, 4, 5. 5 wells, I think. So where do we have the test header and the production header? Okay, which one is the test? The left one. The small one. Yes, okay, this one here. Where do we have? That's the production header and the routing or isolation valves here. So if I want to send a well to production, open, and this one close, opposite. If I want to send to test, this one open, this one close. Right? Okay, so let me just copy these images for you. Okay, these are onshore. We're going to talk a bit about offshore, okay, because you have also offshore fields in Mozambique. And I think you should be familiar with the technology for. So we have basically two types of wells. Okay. We have wells that we call standalone or very close to standalone. That means they are producing close to a separator. Okay? That means if you are, let's say, if you're producing a field, okay, you have a reservoir, you have, let's say, you have two wells, right? And they are either they have their own separator, okay, or the distance from, like, the distance we were showing here, they go to a same header, but the distance is very short. So essentially, it's like if they have their own, they behave like if each one of them was connected to their own separator. Okay, the pressure of the header. So let's call this the pipeline. Pipeline. Or the pipeline is very short, such that P header is very close to P separator. Okay. The pipeline is very, very short, such that I can say, well, all of them have the same header pressure, all wells, okay, because the pipeline is very short, and essentially it's like it has the same effect, like if I was producing each one to their own separator. And that's very common for some fields, okay, for some fields in different parts of the world. I'm not sure here if you have this arrangement, but but you have that they put separators, like in the US, for example. Okay, all of these shale oil wells. Each one of them, usually you have either one separator for many, or you have each one of them have their own separator, and then I load it into a tank, a storage tank, and then I take it into a truck and send it further. Okay, and then we have the other configuration, which is network. Okay, wells in network. So in this case, the separator is far away from the wells. It's not very close. You don't have its own separator, but it's far away from the wells. In that case, the pipeline collects production from many wells and transports to processing. Okay, and if I'm going to make a very simplified drawing, I have one well here, then I have a flow line, connect to a pipeline, then I have another well here, and the pipeline continues, I have another well, maybe I have two in the same place, until I reach my production separator. Okay, and that's what we call a network or a gathering system. So that might be the case for example, some fields where the reservoir is very spread. Okay, I cannot build all wells from the same place. So I have to make one here to drain that area, one here to drain that area, two there to drain that formation. And then the facilities are not for each one of them separate. You have it in one common place, in one place, okay, which is usually close to a port, some place where I can ship and I can export that oil and gas. And you go with a pipeline, you go collecting oil and gas from all the wells towards that facility. What? Processing. Okay? So just the point I want to make here, they are going to behave very different. Okay? If you have them like that, they are going to behave like each one is in their own kingdom. Each one is flowing alone. They feel very comfortable. Okay? No, it's like if you were driving your car by yourself on the highway. Okay? I don't feel anything. If you are here, each well has to compete in the same pipeline for space. Okay? This one, which is far away, has to flow, has to have more energy, has to overcome more losses. This one that is close has it easier. So here we have an interaction between wells. That's something that we have to take into account. Okay? So in the first part of the course, we're going to be focusing. Yes?
So you say that the transport to processor, but there is some production
To processing. Processing actually is missing some word. Processing facilities. Okay? The separator. That will talk later. So that's where we separate. So in the first part of the course, we're going to talk about wells on that configuration, and later we're going to see how do we deal with wells in this configuration. Okay? Because here, for example, if I close production from this well, maybe this one will flow much better. Okay? Or the same there. Here, if I close the production from this well, okay, I don't see any change. So that's okay. Any questions so far? It's a long introduction to start to okay. Yes? Standalone, yes? Oh, the name. standalone por sí mismo. It's just by itself. Okay, it just doesn't have anything else. And that happens, just not to confuse you, but that happens if you have an offshore field. Okay, if you have, for example, in the US, each well is very easy to access. You make an access road. Okay, you make a tank for each as a group of wells or for one well, and then you can come and load it in a truck and send it to the market. Okay, it's connected. You have roads. It's very easy. Or gas, for example, you just connect it to a pipeline and then you send it further. This one, for example, it's we were working in a field in the Amazonas. Okay, was in the middle of the jungle. So, and that was so this was in the middle of the jungle. Here you have a river, okay, not here. Okay. That was the best access point to come and take that production, okay, to come and take it with a boat. Okay, so in that case there was no infrastructure, no roads. You had to cut, if you want to make a road, you have to cut a bunch of trees. So it was no point to make one separator to collect it, because otherwise you cannot come with a truck and collect all of that. The best option in that case is to have a pipe. You just make one opening in the forest where you pass your pipeline, you connect it, you separate oil and gas, and then you take the oil further on the river. Okay? Yes? Yeah, we will see. It's the same. Yeah, it's the same if you have a gas well. It's the same if you have an oil well. Okay, it's the same system. Okay. The thing is that the well will look slightly different, and also the facilities will produce slightly different, will look slightly different, but it's the same configuration. Okay, basically. Okay. So just to make a comment on offshore, I think offshore is going to be very important for Mozambique in the future. Okay, like in offshore, for example, sometimes you have platform wells. Okay, you have a structure, it looks something like that. Okay, and then you drill these wells from the platform. Okay. Okay, to reach and to drain the reservoir, which is someplace here. Okay, in that case, those wells are going to be just so close, they are going to be sharing the same header, that they are going to behave like if each one of them was a standalone well. Okay, offshore. We have here, and we put maybe a fish, just that you know that it's offshore. Okay. Then the other thing is that there might be two cases, either that the water height, the water depth is very high, okay? When we talk about more than 600 meters, okay, we usually cannot use that. The platform will be too long, and then it will have a lot of issues with vibration, all kind of things. So you have to use floating structures. So one of them is like using an FPSO, where you have here the separator, okay? And then you have your wells are on the seabed. Okay? And then I have some sort of collection system. Let's make it here. That collects all of them and takes it to the separator. Okay? That happens if you have higher depth. Also, if your reservoir, you cannot drill all wells from the same location. Okay? okay, if it's very spread or you have different accumulations. So you have to use like a network type approach, which I already mentioned has this one, each one behaves separately. They're king, they are in their own highway, they can do whatever they want, unless there is traffic, right? But here you have a lot of interaction between the wheels. So you have with that we have to be careful. Okay, so if that's clear, I want to introduce I think this is the most important concept in production engineering. Okay, if you understand this concept, so we are going to spend some time to making sure that you understand it. I think all the rest is going to be very easy. Okay, hopefully. Okay, it's going to be a piece of cake. Okay, this concept is called flow equilibrium. Okay, some people also call it nodal analysis. Some people call it inflow, outflow analysis. Okay. You can call it whatever you want, but I think flow equilibrium is like a very generic name. Okay, that takes that is very generic in nature. So let's go back, okay, to pipes. Okay, something very simple. Just take a horizontal pipe of certain length. Okay, and let's call this point P1. Let's call this point P2. Okay, the flow is going on this direction, and you have certain Q, certain rate going through the pipe. All of you had a course in fluid mechanics, right? Maybe a long time ago, but you remember something, okay? So if, let's make a one case, okay? If I keep P1 constant, somehow, either connected to a big storage tank, connected to a pump, to something, that P1 is constant. What will happen with P2 when I change the rate, when I increase the rate? Let's start with some simple point. What happens when we are at zero rate? P2 should be, no, equal to P1, right? I have a horizontal pipe, I have no flow, yeah, nothing whatsoever. So here I should have, let's put it someplace here, P1, okay, exactly at zero. Now, what will happen if I increase the rate, let's say here? Will the pressure be lower than T1 or bigger than T1?
One would be
P2, sorry.
lower than
Lower, okay? Because how do I calculate P2? I start from that pressure, right? And then I go on this direction, taking out the friction losses, right? When the flow is going through the pipe, it's losing energy due to friction, due to the friction with the walls, okay? Therefore, if I'm here, I have, the pressure will be less than P1. Yeah? All of you agree? Hmm? Yeah, condition to have flow. Otherwise, you cannot flow that Q. That's correct. Okay? So this curve, I'm going to call it the available pressure at the pipe outlet. Okay? It's like the available energy that I have at the pipe outlet. If I have a point with fixed pressure and I try to flow certain rate, that's the pressure that I get at the end of the pipe. And the way I calculate it is co-current, concorriente, with the flow. I go with the flow from a point of fixed pressure, and I then reduce it until I find it. But I go with the flow. I start reducing the energy until I reach the exit. Okay? Co-current. Now let's make another experiment. Okay? What happens if I keep P2 constant? Okay, how will P1 look like? Exactly the same pipe, exactly the same system, but now I just want to see the opposite. I'm keeping P2 constant, and I want to see what happens with P1 when I increase the rate. Again, if I have 0, here it should be P2, right? Okay, so when I increase the rate, it's increasing, all of you?
Yes.
Yes? Agree on that? Yes? Okay, because, why? You have to have a higher pressure, right, upstream the pipe, just to be able to flow that rate, a higher pressure. So that curve will look like that. And this pressure I call the required pressure at the inlet of the pipe. Okay, and this curve is calculated counter current. Okay, is against the current. Okay, I have to go see where the flow is, and then I have to go in the direction against the flow. That clear? Yeah, it was easy, piece of cake, right? So now let's see our system that every production engineer, you have to make this drawing. I wake you up in the middle of the night and you have to be able to make this drawing, okay? So we have a reservoir. Yep. Okay, I'm analyzing that system. Okay, so I'm going to ask you how, if I go now to PWF, okay? From PR, if I look only at that system, from PR to PWF, what kind of curve does it look, or which system does it look like? Does it look to case 1 or to case 2? Okay, if we are looking now, the flow from reservoir to PWF, right? What does it look like? What does it look like? Does it look like case, this case, or like this case? First case, right? I have a pressure, which is, I say is constant. It will change with time. But if you take it today, or you take it 2 minutes after, or you take it tomorrow, it's not going to change much, right? Maybe in a year, it will change 2 bar, 3 bar. But now it won't change much. So this one is more or less constant. Then I flow with the current, okay? You're reducing the pressure until I find PWF. Okay? So how is the curve going to look like if I plot PWF? PWF versus Q. Okay, like this one. We don't know yet about equations, but we know if you use the same analogy that we use for the pipe, it should look something like that, right? And what is the point 0 here? Reservoir pressure, right? If I have no flow, I just get reservoir pressure, the same pressure around the reservoir. Okay, that curve is something that we call IPR. Okay, Inflow Performance Relationship. Okay, is the in our language, the available pressure at the bottom of the well, okay, departing from the reservoir. So that's the available pressure. Now let's say that that distance, right, is really, really short. Okay? So we can say that P wellhead is very, very close to P separator, which is constant. Okay? How do I keep the pressure constant in the separator? Which valves? Let's draw a separator first. Okay? How does a separator look like? It's a big vessel. Okay, we have two lines coming out, one for the gas, where we have a valve that we can adjust, okay, like a needle I can take up and down. And here I have Q gas and Q oil. Okay, I have a level. The level is someplace there. So how do I make sure, or what makes sure that the pressure is always constant? And I have here a pressure transducer. And here I have, of course, the flow from my wells. Okay. One thing I have this pressure, right? So when that pressure starts to increase, that goes into a box, okay, into a controller. That is just going to, and here I have a set point, that's very P separator set. Okay. And the difference, if there is any difference, that will tell me to open or close the valve. Right. Now, what about the liquid? If it comes a lot of liquid, suddenly. I have another system which is a floater, okay, a level controller. So if that level is going up, for example, that goes again to another box where I have a level set, okay, here comes a level, let's call it H, okay, H set, and that's going to move that valve, right? So those two controllers, level controller and pressure controller, is what makes sure that my separator is always at a constant pressure. It can come anything. I can change now the rate, high, low, can fluctuate, doesn't matter. That system should be robust enough to keep my separator pressure constant, no matter what. Okay? Of course, it's not exactly like that. We are just, simplifying a bit, but we have a bunch of those working with separators. We have actually a few layers. So that's the low level, upper low level, lower upper level, and upper level. Okay, complicated. Upper level, lower upper level, upper lower level, and lower level. Okay, because it's usually I want to be around these two. Okay. Don't want to be exactly one number, but if you fall between these two, it's fine. Because I have to make sure that no gas will come into that line. If the level is too low, then I have to start to having gas going into the line. And that line was not made for that. Okay. Or I can start if the liquid, if the level goes too high, then I might start having liquid going to the gas line. Okay. So that's why I have these two, it's like a fan. And when it reaches here, I have like an alarm, or I have a certain mechanism, and when it comes here, if it goes below that number, it just shutting down the production. Okay? Just because then the separator won't manage to separate, and you will have oil and gas. Okay, so the whole story was to tell you that separator pressure is constant. So we go back and we look at this system, okay, all the way to the same point. What does it look like, that system? To going back to our discussion up here, does it look like our case to the right, or this case? This one, right? Because I have a pressure constant at the discharge of the pipe, and I want to calculate the pressure at the inlet of the pipe. So how the PWF is going to look like when I calculate it from the system 1? From the system, let's call this one 1 and this one 2. It's going to look something like this, right? And that we call, in that case, if we are just considering the flow line, okay, the tubing, I call it TPR, Tubing Performance Relationship. Okay? Clear? Okay, we will see now it's not exactly true for, when you start having multi-phase flow, start having other things, but I just want at this stage, just conceptually, you make the analogy to the pipe, and you see that, that it also works. And the reason is we have two, in every well, in every production system, we have two boundaries of fixed pressure. We have one boundary in the reservoir, which is not really fixed, but it changes so slowly with time that we can say at one point in time it's constant. And today, next week, it will be constant. And the separator is always constant. That I never change. Okay? So I have two, and I can use that analogy. Go any point that I choose, okay, I can go and calculate pole current, the available pressure, and I can calculate counter current, the required pressure. Okay, so before we take a break, why? So does it mean that I have two pressures in this point? Yes? No, right? If I look here, exactly instead here, I go there, and I say, well, from this point, I have this curve, right? And from this point, I have the other curve. So the only place, or the only feasible pressure for that system to operate is when both of them are the same. Yes? They cannot be different. They are in the same place, just 1 millimeter to the left, 1 millimeter to the right. So the only point where they can operate, these two curves, is exactly here, when the two of them are the same. Okay? Yes? Okay, so that's the whole. So that's what we are going to work on the whole course. Okay? Just we will see okay how the curves look like, how do I calculate these curves, how do I calculate the equilibrium. But if you keep this in the back of your mind always, what am I doing? I'm calculating pressure from here to here, calculating pressure from here to here, and they have to be the same. Okay? If you keep that, that helps really a lot on the when we go to the equations to the more complicated. That here? What happens if I make the equilibrium here, in the middle of the tubing? I don't do it at the bottom hole, don't do it at the wellhead, but do it here. How the two curves will look like? One from here and one from here. It's the same, right? The only thing is that the curve, if I make it here, one curve will be like scaled down, right? Because now I had to reduce even more the pressure. Now the available pressure is going to be less. And the required pressure? Okay, it will be less. You require less pressure. Yes, something like that. Yes, when I have overflow, I should have the same. Is it like that really? No, right? Because now I am adding a section of tubing. Okay, so I have to be.
Yes.
So now I have to ask you something. The intersection I made here, should it give you a different rate than the intersection that I made here? Yeah, the intersection that I have here. This intersection is operating rate.
Yes, it's constant.
Should be the same, right? So it doesn't matter where I put my point, if I put it here, 1 meter up, 1 meter up, if I put it here, even if I put it here, it should always give me the same point. Because the system, if I put these two things together, it will have only one equilibrium point. Okay? Yes. So we take a break. You think?
Just one moment.
Yes.
Just one simple question. The same graph we put here.
Yeah.
Here go first.
Yes.
And for the second graph,
What is that pressure? So that will be separator pressure plus the hydrostatic column, either foil or gas, whatever I have, separated with the bottom. Let's say that I have just gas, right? And I stop the flow of gas. This curve I calculate just by looking at this system. Okay, when I have no flow, this pressure will be constant, this separator plus the hydrostatic column of gas that I have in my flow. So that will be your pressure. Okay, so that will be P separator plus in a row average times G times yeah, we can say TVD. Okay, true vertical depth. Do you need a break or you can continue a bit more? Huh? Break. Okay. We take a break, let's say 15 minutes, and we come back. Okay. Um, just I think that just to put the name, when you have this situation, you call it okay. That's called gas blow by, and that happens. That's why you have this alarm here. Okay, the lower level alarm. Okay, when the liquid level is reaching that level, you will have probably gas blow by. So you just shut down the system. You just stop production. And then the other case, if you have the liquid level is very high, okay, you might have liquid coming in, and that's called liquid carry under. Okay, and that is related to the alarm on the upper level. Just to put the name there. Okay, just I think we shouldn't. If you have any questions regarding this, I think you should, we have to make a better discussion because that's fundamental for something that will come later. But on the pipe example, was that clear? Yeah, crystal clear for everyone.
for it. Yes.
You have to take, yeah, both. It's challenging, but we will see, to control the rate, we will see a bit later. Okay, but just assume that we somehow, God provided, we are God, and we are controlling pressure and rate, both. We are not controlling the three, but we are controlling pressure and rate, somehow. Okay, we will see later how do we control it. But the two curves are linked here. Okay, how are they calculated? You start fixed pressure, calculating the pressure here. That's what gives you that curve going down. And here you start fixed pressure here, and then the curve goes up. Huh? Was it clear? Yeah. Okay, now we go try to apply that very simple concept that was only applied to a horizontal pipe we want to apply it to our most common system or most common problem for a production engineer, which is a well. Okay. First, we have to detect where we have the constant pressure in our system. Okay. There are two clear points. One, which is the reservoir. That pressure is not very constant, but it's changing very, very slowly. The other point is separator. We discussed a bit how the pressure is kept constant. Unless something happens to this control, unless I come and I put some oil or something and break this control, that's going to work always trying to keep that pressure constant. Okay? Now I can select any point from here to here, all the way to the separator, any point. And we're going to discuss that how do we select the point. Okay? But now let's assume that I'm just choosing arbitrarily this point here at the bottom. The method is you go from the two boundaries to the same point. Okay? To go from this boundary to that point, I go in the direction of the flow, right? But here I have to take into account for all the pressure drop in the formation. It's like a pipe, but it's passing through all these passages, through all these porous media to reach this point. Okay? So this essentially is the same horizontal pipe, right? Where I have fixed pressure, fixed rate, okay, and then I find this curve here. And I'm saying, if you do it from PR to PWS, that curve has a name. The industry has given it a name. It's called Inflow Performance Relationship, IPR. We are going to see tomorrow where does it come. Okay, and it goes down. If I have no flow, that pressure is just equal from here to here, and then it will be PR. And then when it starts increasing the rate, the pressure, of course, will drop towards the wood. That clear? Yes? Okay. Now I go from the other bound, where I know the pressure is fixed. Okay, it's separated. Here we're saying the separator is very close to the wellhead, such that the two pressures are basically the same. Okay? And then I go counter current. Remember, the flow here is going up. The flow here is going up. Okay? So I go counter current and I say, well, first no flow, right? So here I have no flow, will be separator pressure, and I go down. Remember, I'm not looking at all at any of this system. I just took it away. I'm just looking at the pipe and the separator, nothing else. I don't care if I do zero rate, what will happen here. I'm just taking that out of the system. And then I calculate, if I have no flow, I just have everything, let's say, is filled with gas, okay, all the way down. And I have here just separator pressure plus the column of gas. Yes? So that's this point here that I call density average times G times TVD, which stands for true vertical depth, okay, of the reservoir. Is TVD. Also another term that the drillers like to use a lot. Okay? So now I say I start to increase the rate. What will be the pressure here? The pressure has to increase because now it's not only the hydrostatic column, but now you have friction. Okay, now due to the flow, you're creating friction. And that curve just goes up. That curve we call TPR, Tubing Performance Relationship. And you see that that simple example of the pipe, the horizontal pipe with the two ends, it allows me to create a curve to represent this part of the system and a curve to represent this part of the system. It's just an analogy, but it's very powerful. Now, I know that if I put these two elements together, it's going to operate at a certain rate, a unique rate. I will have only one unique pressure here. They cannot have two pressures, okay, when I put these two together. So when I put these two curves together, that means that the only input point where this system will operate is here, okay, where the two pressures are the same. Yeah, this curve I created for the bottom hole. Okay, Q star is the equilibrium rate. Okay, and this will be my equilibrium bottom hole pressure. Okay. Now, I don't want to confuse you, but if that's clear, okay, I'm just telling you, it really doesn't matter where I put my equilibrium point, what pressure I'm trying to plot. Okay, if I try to plot P middle of the tubing, P at the wellhead, P in any place in my system, I should get a similar plot. Okay, but we're going to have an exercise, so don't be concerned. But just have the idea that if I decide now another point here, I will have two other curves, but it's the same system basically that I'm joining together. So I should have the same equilibrium point. They should have at the end the same rate, right? But if you, that we're going to have an exercise. So don't worry if you, it seems a bit strange. That here?
This, the hypothesis, that one, the red one hypothesis.
Yeah, that's what I don't want to explain. Okay? Just because we're going to do it in class. We are maybe today, tomorrow, we're going to move the point. And you're going to actually, you are going to show that the intersection is the same. Okay? But for that, you have to do the analysis.
What is giving us the production is the equilibrium point.
Yeah. If you think about it, it's like a curve, or this will be the supply. If you talk about the economy, right? We have here one that likes economy in class, that is working with economy.
No.
Okay, so we have the supply curve, we have some pressure, some energy that we can provide, the reservoir can provide, and we have the demand curve, what it needs to flow against that separator pressure. And you will have equilibrium only when the two are the same. Why? Because if you are here, right, you have more supply than the demand. So the rate starts to increase. It's like you becoming richer. Okay? If you have more money than what you spend, you say, well, I want to spend more money, buy a bigger house, bigger car, etc. Okay, until you reach here. And if you try to go to the right, then you are spending more than what you have. You're having to, there's a loan, and you say, no, I have to, I have to calm down, I don't have to spend too much. Until I reach this point. So it's the same concept, but about energy. Okay? You have energy available, you have energy that you require, and it has to be exactly at the intersection. Otherwise, I always have this, the rate. If I start here, the rate will increase until I reach this point. If I start here, the rate will decrease until I reach that intersection. Okay, clear? More or less? Okay. Now, there is something that we have been neglecting in this analysis, and something that I hope doesn't confuse you. What kind of rate are we talking about here? What are the units of rate? Yes, volume per time, right? But in this case, the pressure is changing, right? So we are saying the pressure, if I move from here to here, is changing. And this can be 500 bar, 1000 bar, 700 bar, and this can be 200, 100 bar, right? So that Q is changing. Okay, so how do we solve that problem? Okay, that's why in petroleum engineering, okay, if I put, here, let's say a master student, okay, they say they are cheap. I don't think so, but they say they're very cheap. You can put many of them to do different things. Okay, so you put here exactly looking at this part of the system. Okay, you put a mechanical engineer. You tell me how much is flowing through the pipe. What is that mechanical engineer going to tell you? So many mechanical engineers like mass. Okay, so he's going to tell you so many kilograms per second. Period. No issues. And that's perfectly fine. Now comes, you call the chemical engineer, right? How much fluid is passing through the pipe? What is the chemical engineer going to tell you? They like to work in moles, right? Some strange thing called moles. So they say kilomole. Okay. All of these two guys, they're going to get fired from the field. Okay. If they come to a production manager, they say so many kilograms per second, go away. Okay. Far away. You cannot be in this field. Then comes the petroleum engineer, right? And he's saying so many in volume. Okay. A very strange unit, cubic meter per day. How come? Volume is not something that is maintained along the system. Something that is changing, usually volume is a function of density, right? What is the relationship with mass flow? Q equals to mass flow divided by the density. And the density is a function of pressure and temperature. Now they have a trick, right? They say, well, we're not using any volume, but we are using the standard. They put a big S in front. And that means they say, well, I'm saying I have a volume, but that I measure at one particular pressure and temperature. So this volume is measured at P standard conditions at T standard conditions. Okay? And P standard conditions is? Yes, 1.01325. I like to work with, okay? Or 15.14. PSIA, and T standard condition is 15.56 or 60 Fahrenheit. Okay. Be careful, they change sometimes from country to country. In Brazil, for example, they use 20 degrees Celsius. Not sure why. Okay, so they say we solve that problem by saying, well, it's a volume, but it's really a volume that we measured someplace. It's not here in the pipe, right? Because P separator, that pressure can be 30 bar, can be 50 bar, can be 70 bar. Okay, reservoir pressure can be 1,000 bar, can be 100 bar. So it's not measured anywhere in the system. But if I take that volume of gas and in a mental exercise, I take it to standard conditions, I will get some flow. And that's the flow that the petroleum engineer likes to use. Okay? And it has some reason, because when I finally, for example, oil, right? I take it through a lot of separator stages, and then I finally put it in a storage, which is at roughly standard conditions, right? So that's why he likes to have the volume in standard conditions, because he just wants to make a very simple math. Okay, he wants to say, well, I have my rate of oil and multiply times 80, right, US dollar per barrel, and that's my revenue. That's all, just for a very simple reason. So that's why they fired all the other guys and just keep the standard conditions. Okay. So the long story is to say that this Q is usually in standard conditions. Okay. That's what we use. Q at standard conditions, which is just like another way to say, it's the same thing that to say mass flow, to say molar flow is the same thing, because it's volume together with two conditions, with pressure and temperature. Yeah, we will see now how do we Yeah, solve that problem. Um, um, okay, now what's the other challenge that we have? And that's something we have to solve very quickly. How do we calculate pressure? Remember, here a lot of the losses are due to friction, okay? Either friction, flow in porous media, friction due to flow in pipe. So what do I have to use there to calculate friction, pressure loss due to friction? What do I need? Yeah, Darcy, blah, 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 but I need, right? I need the velocity, okay? That's the first thing I need. The velocity is how fast the fluid goes in the pipe, and that tells me the shear it has with the walls. Okay? So, and to calculate velocity, that is Q divided by area, right? And that, again, is M divided by density times, which is a function of pressure and temperature. Okay, so I'm still obliged if I want to calculate pressure drop, I have to use local velocity, okay, local velocity, local rate. I have to calculate the local rate. Okay. Now let's make an example with gas. Okay, let's say I want to start with gas because it's I think it's a bit then to go to liquid is much more, and multi-phase is much simpler. Okay, so let's start with gas. We're going to have a discussion on a short discussion on gas. In gas, I'm saying the mass flow at standard conditions, right, of my system should be equal to the mass flow at any pressure and temperature, because it's just mass flow, right? So the mass flow at standard conditions, I can say that is Q at standard conditions times the density at standard conditions, sorry, Q without the hat. That will be equal to Q at any P and T times the density at any P and T, right? That rate is the one that I measure at the surface. That density is the one that I measure at the surface. And this is the Q and the density along any place in my well. Okay, from the formation, even in the reservoir, all the way here, that's my Q. Okay, so here we need this one, right? Need to calculate pressure drop. And I have this one, that is the one that I measure and solve. Okay, and where I want to make all, because here when I make the intersection, for example, I have multiple Q's. I have multiple local Q's. So it doesn't make sense to make the intersection with any of these local Q's. I have to make it with one unique Q that doesn't change, which is the Q as standard condition. Or make it in mass flow and then keep me away from the company because they don't like mass flow. Okay, so I do it in Q standard condition. So a way to relate those two is by using this expression, right? I'm just saying the Q at any point, pressure and temperature, will be Q at standard conditions times the density at standard conditions, the density at P and T. Okay? That clear? Yes? So how do I call this factor? You know, we are petroleum engineers, we like to put names to everything. Okay? So how do we call that factor? We say that Q at pressure and temperature divided in Q as standard conditions is equal to BG, pressure and temperature. Okay, and that's what we call the gas volume factor. I guess you had that before, right? Okay, and that volume factor, if P equal to PR and T equal to TR, then is called formation volume factor, okay? Gas formation volume factor. We are in production, we like to calculate friction every place or pressure losses every place. So that's why we want to make it generic at P and T. So how do we find this factor? We know this factor will be PG will be equal to the ratio between the densities, right? So it will be density at P and T divided by density as standard conditions. Oh, the opposite, right? The opposite. Okay? You have to sometimes make sure that I'm not making any mistakes. Okay. Yeah, so how do I express, what is the way that I can express that density? Density, yes. Density, we know something that a bunch of guys were working, right, since the 1700s. That we call it the ideal gas law or the real gas law, right? You remember these guys? So one of them was Boyle. Yes, I think I have the picture. You have to put some color to the slide. We can see we have some British guy, this guy. And we have Hooke. Okay, they were the ones that were doing experiments, how gas behaved. And then we have that guy that looks very serious. That's, who is this guy? Hooke. These were two British guys, and actually Hooke was like a lab assistant of Boyle. Okay, so Boyle, he didn't spend himself time in the lab, but he said, you do that, like manager, okay? Like jefe. And then Hooke was the one making the hard work, making the measurements. Then you have, who is that guy? No idea, right? These are a bunch of French guys. Paste it here. I think that's Charles. You remember some Charles sounds in the back of your mind. He found that some volume was equal with pressure. Charles. French guy. Then came this guy, which looks a bit more academic. Gay-Lussac. Yeah. And this guy who looks a bit scary. He's like the least handsome of all of the bunch, but maybe the most clever, who knows? Okay, that Avogadro. Okay, and all of these guys, they came with a very useful tool, okay? What was the equation? The equation said PV equal to RT, okay? Where R is the universal gas constant divided by the molecular weight of the gas. Okay? And they say, well, you can really model any gas, any behavior of any gas with this expression called the ideal gas law. Okay? But then came say, well, it deviates. Actually, it's not so ideal, but it deviates. So people came up with a real gas law that is exactly the same, but now they stick a factor called Z, the deviation factor, to account for the deviation with the ideal gas law. Okay, I stick a factor there, a constant, and then I try to map what happens with that factor. So they did some measurements, okay, of Z in the lab with pressure and a constant temperature. So the C goes something like that. First, when you increase pressure, it starts going down and then goes up. That's for a constant temperature. Okay. The thing is that for another temperature, well, it behaves differently. It behaves maybe something like that, T2. Then for another temperature, then it behaves something like that, T3. Very difficult to make a trend. But these guys were clever and saying, well, how can we solve that problem? We want to have an expression that really doesn't matter, and that depends for the substance, that depends on many things. Okay, that was different for every substance. But they came with this principle, very powerful, to try to make a dimensional this pressure and temperature with something that called the law of corresponding states. Okay, they say, well, let's make the same plot, but instead of making it with P, we're going to make it with PR, reduced pressure, a quantity that I call reduced pressure. What is the definition of reduced pressure? Pressure divided by the critical pressure of the substance that I have. A reduced temperature, pressure, the temperature divided by the critical temperature of the substance. And by doing that, all the measurements they had for all substances, they collapse into one plot. Okay, fall on one on top of the other. Big success, big hurrah. Okay, and they came with the chart, with the, we don't want these guys anymore, this chart that I guess you know how to read it. Or maybe we need to make a small refreshment. Okay, but then by making that, here you plot the set. Okay, here you plot the self-reduced pressure, P divided by P critical, and these lines are for one critical temperature, one reduced temperature, 1.2, 1.25. This line is just to make it, you see that here the scale goes, maybe you cannot see it, I can barely see it, okay? But here is 0.25 to 1. Okay? And for the rest is just not to make all of them overlap in the same plot. Okay, so here you have for the range from 1 to 1.1. So is that upper range that was there? They put it. Okay. For higher, sorry, the scale is wrong. It's here the scale. Okay, so you have the zero reduced pressure. If you go from 0 to 8, you use this upper plot. Okay. And if you use 5 to 7 to 50, you use the lower part of it. And they have the same reduced pressure. Okay, so that's what we are going to use to calculate the BG. Okay, that's the first exercise we're going to make today. And maybe, I'm not sure if we will have time for another. Said usually in production and in reservoir goes typically is in the range between 0.7 and all the way maybe to 2. Okay, that's maybe too much, 1.8, 0.7 to 0.2. So you can have a correction up to 200% of the value from the ideal gas law, and 30% from the minus 30%. Now, in reality, that's very nice. Okay, we have it for methane, for any pure substance. But you know that in reality, what we produce, every gas that we produce, we are talking here only gas, right? Every gas that we produce from our well is not any pure component, right? It's not either methane or ethane, but it's a mixture. So how do we deal with that if we have a mixture? In reality, of components. Yeah, and for gas, typically we have methane, ethane, propane, butane, maybe we even have some pentane, and we have some heavy components. Okay, and we have mole fraction. Okay, we have some mole fraction XC1, XC2, C3, C4, C5, C6. Okay, so how do we deal with that? How do we use this diagram for this mixture? Okay. So one thing that was done is that some people say, well, let's compute for this mixture an average molecular weight of this mixture. Okay, you know that each one has their own molecular weight. Okay, methane 16, propane something different, okay, so forth. So they say, let's try to compute something that will characterize the mixture. Okay, that will characterize this mixture. And let's use the molecular weight. So the molecular weight of the mixture will be equal to the sum of from I equal 1 to n, where n is the number of components, of xi molecular weight I. Yep, I'm just summing all of them, multiply by how much you have in the substance. Okay. The next step they made was, well, let's then say, you know that the specific gravity of the gas is equal to the molecular weight of the mixture divided by the molecular weight of air. Okay? So I can calculate that, and this is 28.97 molecular weight of the mixture. And then they say what we really need to use the same chart. At the end, I want to use the same chart. I just need the critical pressure and the critical temperature, right? To calculate, if we have that, we can calculate the reduced pressure and the reduced temperature. Okay? So then I made a correlation that said the critical temperature of the mixture has a function of the specific gravity of the gas, and the critical pressure of the mixture has a specific gravity of gas. And this was a researcher called Sutton. Big success. Okay, now, even if I have a mixture, even if I know I cannot use it one by one, I just take a number that characterizes the mixture. That is the average specific gravity of the average molecular weight. And after that, I use a correlation. Someone was in the lab measuring one mixture by other mixture by other mixture, and finding saying, well, if the mixture has some specific gravity, it will have this critical pressure and this critical temperature. Okay, then I can calculate what I need to use the same set. Okay, now we have one more step before we go to the exercise. That we have this expression abandoned here. We have to use that. Okay, we said Vg will be at pressure and temperature, will be the density. How do I express the density in standard conditions? Okay, remember P standard conditions, V standard conditions equal to R times T standard conditions. Okay, but density as standard conditions is 1 over V standard conditions. Yes? So this, you can express it as density as standard conditions is P standard condition over RT standard conditions. Yes? And what happened with the set? Why did I take it away? What happened with the set? Why did I take it away with the deviation factor? Because it's 1, because the pressures are very low and the temperature is also very low. So this is very close to ideal, is very close to 1. Okay, so up here comes PSTSC, and then I need the density at local conditions. So that will be using the same logic. Okay, pressure, RT, and set, right? Is that correct? So I have P, RT set, and the R goes away, right? The R cancels each other. And that tells me that the BG is just a function of a constant TP times set. Okay, and here I have that set that I need to calculate from for a mixture. Okay, remember here something careful. Temperature has to be in absolute. Okay, so either you use Rankine, you use Kelvin, but you have to use absolute, an absolute unit. Okay, and pressure really you can use, but it has to be absolute also. Okay, you have to use absolute either bar or either PSI, but you have to use. Okay, so the next exercise we are going to make, you are going to make, okay, we are going to have in this well, so we have done, okay, we have a well, let's paint a well. We have our tubing, okay, and here we have our valves, okay, and we have open our master, here is closed, okay, the wing valve is closed, and we have sent an equipment, we have sent a wire line through the well to measure at different positions, at different TDEs to measure pressure and temperature. Okay, from the top of the well down to the, well, it's not closed, it's flowing, sorry. That's, is not closed. So you have some flow here, Q flowing. Okay. And we have measured for different TBDs. So you got a table saying TBD, TBD1, TBD2, TBD3. Okay, or actually, it should be better if it's MD. Pressure and temperature. And they are afraid that this well might be having erosion. Okay? That the velocity is so high that it's just starting to take material out of the walls and it can create all kind of issues. Okay, a hole in the tubing can cause corrosion, can cause erosion, many different things. Okay, so they just want to verify with these two numbers what will be the velocity. Okay, and for that we're going to use the BG. So to get the data for the exercise, you can go, I hope you brought your laptops, right? Your computer? Otherwise it will be very boring, just me showing you how to, okay? If you don't have, you can partner it up, but I recommend you to bring it for the next days. So if you go to this website, okay? Just www.ipt.ntnu.no, It's a snake, stanco-files. You will find three exercises. And the one we're going to solve here is number 2. ntnu.no snake You get it? I think my writing is not very good, right? They're having some issues with my handwriting. ntnu.no/stanco, my last name, files. Just go quickly on your computer just to see. The file should look something like this. No. In the folder on the website, you have the exercise 1. Okay, exercise. Those you're going to deliver. I think we said last time a week after I left. So I'm going to leave. It's on the 11th. So let's say for this weekend. Okay, for the 18th of November, you have to deliver all exercises. Last time we had around 6, I think, or 7. But many of them are going to be solved in class. So that's why I wish if you bring your computer and do it while we are doing it here. So then you don't have that much work at home. Okay? The first one is very simple. It's similar to the one that we did here, or that I did here, just to try to, you have to connect to 2 headers. Okay? With two different wells, 3 different wells in that case. So you read through it. And if there are any questions, we can take it tomorrow. But let's go now to the second exercise. That should look something like that. Okay? So you have measured at the surface the gas rate. Okay? You see standard. You see the S before. Let me put it bigger. Okay? And we have the measurements that were made. In this case, the welded pressure was very low. Maybe it's very close to a separator. And then you have measurements at different depths. They're not provided here. And then the temperature. So we want to calculate for each one of them the local rate of gas as a first step to start calculating friction, etc. All different things. Okay? But for that, like I already mentioned, the VG, you need the VG to calculate QT. And to calculate VG, you need also SEP. Okay? It's deviation factor. If you remember the definition, okay, you see VG depends on pressure, temperature that I measured, but it depends on SEP, this deviation factor. Okay? So when you open the sheet, if you have any message saying there are some macros, you have to click enable. Yes? How many of you have worked before with macros in Excel? Macros in Excel or VBA module? Okay? So let's do something. Let's solve the exercise first, and then I show you how do we solve it. So this chart, okay, in principle, you should have to come here. So what is the first step? The first step with this gas gravity, you have to compute these critical properties, right? PC and TC. Then with PC and TC, you calculate PR and TR for this line only. Then you come to this plot, and then you use the TR and the TR, and you read the set. Okay? Then you type it here. Then you type it in VG with pressure, temperature, and set. And then you finally compute QT. Okay? So we are going to do it a bit different. This chart has been already pre-programmed for you in Excel. Okay, Excel you can do programming. So let's try if it works. Just try, in your case, go to this FX you have here on the window, FX. Go to user defined. On the menu here, you select user defined. And then you go down all the way where it shows set C factor standing. Is it working for all of you? Comme ci, comme ça? Okay, I come here, FX. I have to be standing on the cell where I want to apply this equation. Okay, press FX. You see, if I click there, it says insert function. Okay, then I go, then I click on user defined, something that Milan defined, in that case for you. Okay, C factor standing, and double click on it, or click OK. And you see the following input. No? Okay, so here we are going to say, we're going to do everything that I told you at the same time. Okay, so don't be confused. We have to, with this number, calculate critical properties, pressure and temperature, then we calculate reduced properties, then we go to the chart, and then we reset. All of that is going to be done here. And I'm going to show you later how it works. So first we select pressure, okay, this pressure. Then temperature, this temperature. Okay. Look here, it doesn't say anything about the units. So you have to trust me, I have to tell you the units are correct. Okay, but we will see, you will see later, you have to be smart and how to check with the units. Then specific gravity of the gas, I have to click here, but you will see later, we are going to apply that function here and here and here and here. Okay, and the way to do that, we are going to drag this expression down. So if we drag it down, it will take now this pressure and temperature, this pressure and temperature, but it will also take this specific gravity, this and that. And I don't want that to happen. Okay, and I drag it down. So what I'm going to do, I'm going to block it, and I block it with F4. If I press F4, it should appear the dollar signs in front and behind the letter. That means it's going to be blocked. No matter how I pull that function, it's going to be blocked. And then unit, you have to trust me again, you have to put 2. Okay? And see the number that you get. You should get, in my case, 0.948, which makes sense. Okay? We said the deviation factor is something around 1, 0.7 to 1%. Yes?
Why unit 2 is something that is embedded?
Yeah, we will show you. I will show you. Just give me 10 minutes, okay? Yes, and I click OK. The convention we are using here, you see, red is for data that I input, okay? And blue is data that is calculated somehow. So now to drag it, I go to the bottom of the cell until I get the cross, and I have either to double click, or I can also take it and drag it down. Okay, and if you see, for example, the second is taking now this pressure, this temperature, but it's taking the same gas gravity as before. Are you getting the same results? Yeah? Okay. Hmm? What's the problem? Okay. So now I'm going to show you with VG how we have done that. Okay. So yeah, I just want you to press Alt F11 at the same time. So Alt first and F11 later. Alt F11. Using a lot of new tricks. Alt and then F11. Okay, you should enter into some sort of this window. Okay? Yes. Okay? So, if you see to the menu to the left, that's showing you all the elements you have in your Excel sheet. Okay? You have, in this case, I just have one sheet, okay, called sheet 1. But here you see I have modules. And here is where I save this C factor standing is actually a function. Okay, a function is like something that takes an argument and then gives you an output. Yeah, and I have programmed myself to exactly what that function has to do. Okay, so if you see function, I declare first saying is a function. Then I have to put the name of the function. That's how my function is going to be identified. And then I have to put the input of that function. In that case, 4. Okay, P1, and I have to put, in that case, that's not always necessary, but I say that's a double, meaning that it's a number that can have 15 decimal points. Okay? Also here, and this unit is an integer. And here you have a description of what each number is doing. So pressure can be a number in PSI or bar. Temperature can be a number in Fahrenheit or Celsius. This gamma G is the gas-specific gravity. And the units, if I select 1, that means that the pressure should be in PSI and the temperature should be in Fahrenheit. If I select 2, it means that the pressure should be in bar and the temperature should be in Celsius. Okay? And inside, I give, you see here, what I told you initially, the calculation of the critical pressure and the critical temperature. That's using the paper by Sutton, this researcher. After I have that, I convert units. After I have that, I calculate the reduced pressure and temperature. And after I have that, I have a very ugly expression to calculate Z. You don't have to understand how it is done, but you have to, this is like equivalent of going in the chart. Okay, but we save all the trouble. We don't have to look for every number in the chart. We have here a utility that calculates the set for you. Now look at the function BG. Okay, And B again, you have units. Okay? Okay, so you have to give pressure, okay, in PSI or bar. You have to put temperature in Fahrenheit or Celsius. You have to put Z, the gas deviation factor. Something also important about function is that the number I want to return has to have the same name as the function. Okay, so in that case, I want BG to return BG, I have to use the same name, exactly the same name. Okay, and here I just have me saying if I'm working in few units, I use this expression where standard conditions are in 14.7. Okay, but if not, I am using this expression where standard conditions are in bar. Okay, so let's use that expression now. We go back, you can punch again Alt F11. Okay, and we do exactly the same way. Click on BG, insert function, user defined. I look for BG, P in bar, T in Celsius, Z the deviation factor, and unit that will be 2. I'm getting a small number of zeros. You're getting, so that number makes sense. with the number we are getting? 2, 2 to the minus 2, right? If you remember, okay, that was the ratio. Let's just do a very quick quality control here. That was the ratio of a volume. We have these guys here. I'm going to have nightmares with that guy. Okay? We have the ratio, that density divided by that density. How is usually the density as standard conditions of the gas?
It's very low.
Okay, it's very low. So let's say air, okay, 1 or something like that. This density at higher pressure and higher temperature, very big, right? Density, when I have more pressure, tends to compress the gas and increase the density. So this number should be always less than 1, and it's usually around that range that we have there, around 1 to the minus 3 to the minus 2, something like that. Okay, then I drag it down for all the rest. Now for the last step, how do I calculate the local rate? How do I calculate the local rate? Huh? Sure?
No, the same way.
Multiply, divide. Multiply what with what? Okay, we said that Q at any pressure and temperature divided by this guy is Vg. Is that correct? It's the opposite of it. So this times that will be the Q at local conditions. Okay, so let's multiply. This one will be this number times this number. And then I have to block V1, remember? Because the tubing has the same rate in all the depths. Okay? Okay? You get the same number? Okay? So you see it has reduced dramatically the volume. It's not the same. It's okay. Yeah. So now let's calculate one more step, velocity. How do we calculate velocity? With something we don't have, the ID. Okay. Let's assume I think this well was 4.5 inch. So let's put here 4.5 inch and calculate the velocity at that position in the pipe. Okay, the gas velocity. So for that, I have to put here diameter. So I suggest we add it here, D, and that will be in meters. And then we have area, that will be meters squared. That was 4.5 times 25.4 divided by 1,000. Okay, and the area is pi times this number squared 0.25 times. Okay, pi times diameter divided by 4. Yep. Is the tubing has an ID of 4.5. That is an exercise you have to deliver. Okay?
You cut the left line.
Huh?
You didn't include the left line.
Yeah, that doesn't matter. It's the same for all. So you see, some interesting observations. So here you have the function called cfact standing. Okay, that was using p, t, gamma gravity, and unit. Okay, here you have the function bg that use p, t, z, and the unit. This one is just the standard conditions rate times bg, and this one is the qg divided by the area, and using this conversion factor, okay, because that will give you in cubic meter per day. So you have to change 1 day is 24 hours and 1 hour is 3,600 seconds. Okay, so you have to multiply by. And we are going to come back to this well later. Okay, but just something to note is that we have to make, so you have to make two plots. That's for the homework. Okay, you not only you have to solve it, but you have to plot QG versus pressure. Yeah? And you will see this QG is just going like that. Okay. When I reduce the pressure, QG is just increasing, okay, which makes sense. And the velocities we will see later, they are very close to the erosional velocity. Okay, so it's very highly likely that you're going to have erosion in this well. Okay, so that's for the homework. You have to make that plot, and that's very important. We need those plots when we go to more complicated cases, multi-phase flow, erosion, we're looking at liquid loading. It's extremely important to plot many variables with pressure or with depth. Okay, in this case, they are equivalent, TVD or MD. The next thing I wanted to make a comment on is BG. Okay, how BG behaves, and that's a classical plot you probably covered in reservoir engineering. BG, if you plot it with pressure, has basically the same behavior as the rate. Okay, it's a exponential type behavior going down, and that's for fixed temperature. In this case, temperature is also changing, so it won't follow exactly the same line, but it has more or less the same trend. So I suggest we stop here, right? It's not good to cover more. Yes. You say the website. You have to take the velocity is the flow rate, local flow rate divided by the area. Okay, and then you have to change the units. So you have to divide by 24 and you have to divide by 3600. Okay? Just one thing, okay, so let's make first a summary. What we covered today was a very long day, I think, and we have many of those to come. So our brain is going to be tired. But we're defining a bit the scope of production engineering, okay? Where are we looking at? Where are we concentrating? And what are our tasks, okay? Then just to get common terminology, we talked about all the major locations in the wells related to production, okay? The well has many other things, but are related to drilling. To production, we only look at casing and tubing, and very important, to control the well, we need these valves that are on the top, that we call the Christmas tree. Then we talk about Christmas tree, okay? Árbol de Natal, de Navidad. Yes, Christmas. It looks like that, okay? So master, lower master, upper master, wing valve, and swab. Okay? If you want to send this wire line, you put something on top that you call a lubricator, another piece of pipe where you send the instruments down. Okay, we are going to maybe not talk about that much. Manifold, very important, is the heart of the system. You can use it for many things, especially the main thing, the money, to split who gets what. Okay, we are poor guys, we don't know, we are not getting any of this money, but the big guys, they are getting this cake, so they want to know exactly how much cake they are going to eat. Okay, we say it looks like that. We say something about the architecture, and we are going to talk about networks a bit later in the course. And we say that can also happen offshore. Okay, that is going to be very relevant for you. Coral, I think, is one field that is developed. So they're going to need engineers that understand how the system looks like. Then this concept, I think, is crucial. It's very simple. It sounds even stupid, but you can use it to characterize many parts of the system. And the equations we will see, they can be very complex. Okay, you can have pump, you can have multi-phase flow, you can have 3 phases, you can have many different things. But if you keep thinking about this type of equilibrium available and required, that's a very good, important first step to solve your problem. Okay, then we talked about standard conditions. We talked about the case of gas and this factor Bg that you might have heard of it for reservoir, okay, something that they use a lot. But for production, we need also the temperature change. Temperature is changing along the system. So we went to see how that factor is calculated, to do a bit of a refresher. How do we calculate it when we have a mixture, which is very important? Okay, we know this guy called Sutton, that he came with this wonderful correlation. Okay, and then we did an exercise about, you have some measurements of pressure and temperature, and we want to calculate velocity. Okay, and you got exposed to Excel. That this function is called UDF. Okay, is user defined function. Okay, and is in VBA, which is called Visual Basic for Applications. Okay, and it's like a programming module. How many of you have used MATLAB? MATLAB? How many of you have used MATLAB as a program called MATLAB? How many of you have programmed before? All of you? Yeah? Well, maybe you use Fortran or you use something ugly like that in the... Okay, Fortran is something in Excel that allows you to make programming. Okay, make your life easy. Tomorrow we are going to make maybe a small example so you know how to create your functions, but it's not really necessary for this course. Okay, I have programmed all functions you're going to need. The only thing is that you have to be aware to understand how the function works. Okay, so what is the input and what is the output, and roughly understand what kind of operations are being done. Okay, just to have a quality control. But you are not required in this course to go and program. I'm giving you the simulator is just to save time. Okay, if you have to imagine how long it will have taken if we have to make every point manually. Okay, you have to go to the chart, it's a mess, then we lose an hour, everybody gets bored, and then you go frustrated, say, okay. We have done it very quickly, and just to show that what we want is not so much the procedure and the calculation, but what are we going to do with this calculation? Okay, that's what is important. Okay, so we close our session. Thank you and see you tomorrow.